Okay, so this chapter, which we kind of briefly discussed, is called Thermochemistry. And thermochemistry is the chemistry, so chemical reactions that involve heat or lack of heat. So it's not just things that get hot, it's also things that can be cold, okay? Like I said, we're going to skip this first little part and kind of jump to what heat is. So a really important part of this chapter is heat, obviously, if we're doing thermochemistry. And heat right now is going to be represented by the letter Q. All right, so this Q right here is going to mean heat. Now here's where you have to be careful, because heat is one word in this chapter, but so is the word enthalpy, and they're not exactly the same thing, and we will discuss their difference later. But for right now, heat is just a transfer of energy between two objects due to a temperature distance. So heat is not the only form of energy. It's probably the most common form we're used to thinking about, but it is not the only form. So this first part of this chapter, we're going to focus on specifically heat energy in the form of heat. And back very, very long time ago, we talked about it being extensive and intensive properties. So an extensive property is something that how much stuff you have matters. It changes that property. So more stuff, more heat. Less stuff, less heat. That's what it means to be an extensive property in terms of heat. And then in this chapter, we're going to learn a new unit. So the heat unit, not temperature, but heat, is measured in joules, which is represented by a big capital J. Or sometimes it's so big, it's measured in kilojoules. Now, for those of you who don't remember, there are 1,000 joules in 1 kilojoule. A kilo is bigger than a joule, okay? So this is a conversion factor you might need, so I'd make note of it in case you don't remember this metric system conversion factor. Now, believe it or not, all of your foods that you eat also have energy stored in them, okay? Now, the energy stored in our food are measured in calories, all right? And by definition, a calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So,
I just got a question.
Uh-huh.
Yeah, so why did they decide to use 2 different calories, like one with the lowercase c and one with like the bigger c?
I'm almost there. I haven't gotten there yet. Okay, so this conversion factor right here, you also need to know. You don't need to memorize it. I'll give it to you, but it's how you jump from joules to calories. It's like, right, we know how to jump from inches to feet, or we know how to jump from centimeters to meters, right? It's just that kind of conversion factor. So what's interesting, though, is the food, like when you read labels on your food packets. Let me see if I can find one right here. I did have something. Well, I'll grab this yucky, nasty Gatorade that we have. Okay, so if you're reading a food label, and I don't know if you can, I don't know, let me see myself. Okay, so right, they give you like fat, sugars, but calories is usually the main thing, right? Those calories are actually not these. The calories on your food labels are actually kilocalories. And the reason that, so here's your answer, Nathan, the reason that there's 2 different ones, like why is there a little calorie and a big calorie? Well, because if you think about it, like look at this Gatorade per bottle is 80 calories, okay? But that's 80 kilocalories. So really, if you were to put the true little calorie on there, you'd have to write 80,000, which would make the labels a lot more complicated, right? With a lot more digits in them. And so they simplified by just assuming, we just assume that these are all kilocalories. Even though it doesn't explicitly say it, the big capital C stands for a kilocalorie. And so that's something you might not be aware of. And that doesn't change like the outcome, like, oh, this is 80,000 calories. It's not 80,000 calories like the calories we're used to. It's 80,000 like little baby calories like the ones that you're not used to that I'm just introducing you to. So it's not like, oh, they're tricking us and this has so much more in it. It really doesn't. That's just, we're used to having these as kilocalories. You just didn't know probably that they were measured in kilocalories. And again, because those numbers would get so big on the label that they just tried to reduce that, okay? So again, your food has energy stored in it, okay? And in fact, you can take something like a peanut and you can light it on fire and it will give off heat because it has stored energy in it, all right? And your body uses that stored energy to do work for you. All right, so in a new equation we're about to learn, I haven't gotten quite there yet, we have something called specific heat capacity. And specific heat capacity is represented by little baby c, I can't write on there, lowercase c. Oh yes, I can, I'm on the wrong one. Okay, little baby c. And it sounds a lot like calorie or joule, where it's the amount of heat required to raise the temperature of 1 gram of one substance 1 degree Celsius. So its units are joules over gram degrees Celsius. The amount of energy to change 1 gram by 1 degree Celsius. And remember, right now, joules are a unit for energy. Now, every single substance has its own specific heat capacity. We will use this one a lot because that is the specific heat capacity for water. Okay, it is 4.184 joules per gram degrees Celsius. And we're going to use water a good amount of times, which is why I'm showing you this one. You will not be required to know every single substance's specific heat capacity. I will give you a chart with them in it if you need it. The only time you won't know it is if you're being asked to solve for it. Then obviously I wouldn't give you a chart, because if I'm asking you to solve for it, you would just look in the chart and give it to me. So we will do an example problem like that in a minute. But every single substance has its own specific heat capacity. Now, here's what I mean by that. Water has a certain number. It's 4.184. Copper has its own specific heat capacity. Nitrogen has its own specific heat capacity. Oxygen has its own specific heat capacity. Why? Because all of these substances are different. So they change temperature at different with different amounts of energy. Now, here's what we have to consider. A metal. We're going to think about copper, a piece of copper, like a full copper penny, okay? And then just water. What do you know is common about metals when you heat them up in terms of how quickly they get hot? Do metals get hot fairly quickly? They do, right? So that's why, like, if you heat a metal for a second, you're like, ooh, I don't want to touch it because I don't want to burn myself, right? That has everything to do with its specific heat capacity. Here's why. Metals have really, really low specific heat capacities. What does that mean? You don't have to put in a lot of energy to get them to get hot, okay? So a small So we're going to compare just two different specific heat capacities, little baby c. Okay? This is a low or a small heat capacity. Specific heat capacity, excuse me. This is a larger relative to one another, okay? Specific. So what does a small specific heat capacity mean? It means I only have to put in 0.57 joules of energy to change the temperature, 1 gram of a substance, by 1 degree Celsius. Whereas for, we know this is water because I just told you it. This is how much energy I have to put into water to change 1 gram of it by 1 degree Celsius. Meaning water won't get hot as easily as whoever this guy is. The less energy you have to put in, the hotter it's getting with less work. You don't got to put in a lot of energy for it to change temperature. So these numbers you often see referred to for metals. Those low specific heat capacities are for metals because they don't take a lot of energy to get hot, right? If I take a piece of gold and I heat it up for 20 minutes, and I take the same amount of water and I heat it up for 20 minutes, who would you rather touch after 20 minutes? The gold or the water? The water, right? Because it's probably not going to be as hot as the gold is, because the gold gets hot much easier. Metals are super good conductors of heat and electricity. So that gold will get super duper duper hot. I mean, you probably wouldn't want to touch either, to be fair. But the gold will get hotter, and that's because it has a small specific heat. It heats up really easily. It requires little energy to get it to change temperature. This is like a low energy. Okay? Now, let's talk about the difference between heat and temperature, because they are not the same thing. And I think it's very easy to confuse them. So remember, the temperature of any substance is the measure of its average kinetic energy. Remember, energies of motion? It's a measure of how fast they're moving. Okay? Temperature is an intensive property. What that means is a temperature, no matter how much stuff you have, if it's at a certain temperature, it's not going to change. So like 50 grams of copper at 100 degrees Celsius and 50 grams of water or 100 grams of water at 100 degrees Celsius, they both have the same temperature, no matter how much the mass changes. Okay? Now, their heat, however, is not the same. So here's my best example, well, not my best, but it's a great example of how to think of them separately. If I take an entire, 50-gallon bucket of water, and I get it to boil. Do you guys remember what temperature water boils at? 100 degrees Celsius. If you didn't know, you need to know real quick. Okay? And then I take the drop of water, maybe like 5 milliliters of water instead of the bucket, and I heat it up to 100 degrees Celsius. First question, are they both at the same temperature? If they're both at 100 degrees Celsius. Yep, they're both at the same temperature, right? Would you rather have the 5 milliliters of water that's boiling dumped on you, or the 5-gallon bucket of water dumped on you? The smaller one, because heat is extensive. If you have less of the water, it's going to contain less heat. But that bucket of water, you have so many more molecules at 100 degrees Celsius, that would hurt really, really bad. Okay? Like really bad. You'd probably be hospitalized if someone dumped a boiling bucket of water on you. A drop, you probably wouldn't be hospitalized. It still might hurt, but not as much because it doesn't contain as much heat, even though they're at the same exact temperature. Okay? So how much stuff you have matters for heat. Okay. So I came up and I pulled up a table of all different substances' specific heat capacities. These are their constants. Again, you will never memorize these. I mean, you might end up knowing water by the end of it because we'll use it so much. But these are just different substances' specific heat capacities. So look, you got water has a pretty high specific heat capacity. It takes quite a bit of energy to get water to change temperature. Whereas look at your metals down here. Iron, copper, lead. Not super high specific heat capacities because they change temperature with a lot less effort. Okay? So, here's our first equation for this chapter. You don't have to memorize it, but we will use it a lot. It's Q equals mc delta T, and we'll talk about the delta T in a minute, where Q means heat, M means mass in grams, C is the specific heat capacity constant, and T is temperature. Now, in the gases chapter, if you remember, temperature had to be measured in Kelvin. Okay? This chapter, because we're subtracting them, you can get away with Celsius, and I will show you what I mean. If you're wanting to calculate change in temperature, the word change, or the triangle means change or difference. which mathematically means subtract. Final minus initial. That's what it means in math. Yep. Thank you. Okay. So if I wanted to calculate the delta T, or change in temperature, for an initial temperature of 20 and a final temperature, excuse me, of 78.2, we're going to calculate this in Celsius first, and then I'm going to show to you what the difference is for if it were to be in Kelvin. So final temperature minus initial temperature. So delta T is T final minus T initial. So change in temperature is 78.2, that was my final one, minus 20. That's it, we just subtract them. So what do you get? 78.2 minus 20. 58.2 degrees Celsius is the difference in temperature. Well, what if we did this in Kelvin? So this was Celsius. What is 78.2 in Kelvin? Well, you take 78.2 and it changes Celsius to Kelvin, you just add 273, right? So you do 78.2 plus 273. So that is 351.2, right? Kelvin. Minus, what is 20 degrees Celsius in Kelvin? Well, you take 20, you add 273, so it's what? 293 Kelvin. What happens when you subtract those two numbers? You get the same answer. So the reason we can use Celsius in this chapter as opposed to only Kelvin is because we don't just have temperature, it's change in temperature. Subtracting them, whether in Celsius or Kelvin, gives us the same outcome. So this will be like the only time all year you can use Celsius, pretty much. All right? Okay. This equation is often referred to as MCAT, MC, because the triangle kind of looks like an A. So you'll probably hear me refer to it as that, MCAT equation. And again, it's Q and mass, and C will always be a constant, and change in temperature. All right, so we're going to practice one. Now, let's start. I know the answers are on here, but let's start by reading and trying to figure out what they're asking for. So it says calculate the specific heat, and you go, oh, here's my equation. Specific heat is this guy. So that should be who I'm solving for. And I gave you 10 grams. Who does this belong to? Mass. Of an unknown substance, and 114 joules of energy. So this is our new unit for this chapter, where joules is heat, or Q. So this is Q. And I also give you a temperature change. So delta T. So we're going to calculate specific heat. So here's what you have to do. You need to rearrange. I'm going to do it over here. So Q equals MC delta T. I need to get C by itself. So I'm going to divide both sides by M. And I'm going to divide both sides by delta T. So I'm going to put delta T down here also. So it's Q divided by M delta T equals C. So what's Q? Well, Q was 114 joules. So that goes on top. Divided by, what was the mass? Mass was 10 grams. And then what is delta T? Again, this means final minus initial. So if you look back in the problem, the final temperature was 50.4, while the initial temperature was 25. So you're going to take 50.4 and subtract 25 degrees Celsius. So I would do the subtraction first before you do this, but I'll give you a second to calculate it out. So this is what I got, 0.449 joules per gram degree Celsius. That is C, the specific heat of whoever this substance is. Now, the question asks you to identify the substance. Well, you can't do this without a chart. I don't expect you to get a specific heat and be like, oh, I know who that is. So if I do ask you this like on a quiz or a test or on a worksheet,
iron?
I'm going to go back to my chart, and we're going to find the one that looks the closest to that number, which was 0.449. That is pretty close to iron, right? So it's probably iron based on this data. Okay. All right. So from this table, you know, if you round this 0.449, it would round pretty close to 0.45, or it would be 0.45. This is most likely iron. Okay. So let's try another one. It says a piece of metal with a mass, so this is M, absorbs 256 joules. Okay, so this is Q. Heat or energy is Q right now. And then notice this wording. It says increases by 425. And you think, I don't see two temperatures, right? The two examples I gave you, it had an initial temperature and a final. That is because this word, increases by, is telling you that this is delta T. 425 is delta T. Okay, and it says, what is the specific heat? Okay, so specific heat is C of the metal. And then I give you the chart and you're asked to identify the metal. So, here we go. Q equals MC delta T. I'm trying to solve for specific heat, so I need to isolate it by itself. So I divide both sides by M and delta T. So the M's gone now, and the delta T's gone. And you have Q over M delta T is C. And now we just plug and chug in there. So it was what? 256 for Q. The mass was 4.68 grams. And the delta T was given right off the bat 425 Kelvin. So you take 256. To avoid calculator issues, take 256 and press divide, 4.68, and then press divide again, 425. And you end up with 0.129 joules per gram Kelvin. So again, that bottom, joules per gram Celsius or joules per gram Kelvin, they mean the same thing. And so given the chart, if we're trying to figure out who it is, 0.129, well, lead is 0.13, which is pretty darn close to 0.129. So based on this data, the metal is most likely lead. Any questions so far? Okay. So when we talk about heat in a system, the system is usually the experiment or the thing we're focusing on, and the surroundings are us, everything around the experiment. So if heat moves into the system and away from us, into means endothermic, okay? and that feels cold to us because we are the surroundings. So heat moves inward away from us, so our surroundings feel cold. Whereas if heat exits, leaves, is exothermic. If the heat is coming out and exiting towards us and heat is moving towards us, it feels hot to us. So endothermic processes feel cold to us, and exothermic processes feel hot to us. Okay? We are always measuring the surroundings. So you put a thermometer in something and you measure its temperature, you're measuring the surroundings. We are always in the surroundings. We're never right inside the experiment. You go, oh, but I put my thermometer inside the beaker I'm doing the experiment in. You're still part of the surroundings. You're not getting inside the molecules. Okay? I'm going to skip this real quick. Oh, actually, no, I'm not. Okay. So enthalpy is close to heat, but it requires considering the moles of the reaction. Okay? So it's really, let me see if I can draw this. So it's really like this. Heat equals NH. Or you could use mass instead. It really depends what they give you for H. Okay? Which means if you rearrange to solve for H, it's really Q over mole is H. So it's Q, but with moles in it. It's Q divided by mole. So it just considers moles. Okay? And our enthalpy is going to have signs, positive or negative values. And those signs are going to mean something. All right? If Q is negative, H, If H is negative, there is no such thing as negative heat. So the negative sign is descriptive. It means heat is lost, exit, given off, exothermic, okay? You cannot have negative heat. There's no such thing. So if you have a negative sign in front of a numerical value in this chapter, it's because that amount of heat is lost, given off, released, okay? Whereas a positive value, which is endothermic, heat is going into the reaction. You're adding positive heat. You're not subtracting heat. Okay? So when heat moves in, it is endo. When heat exits, it's exo. All right?
What does H mean again? Sorry,
it means enthalpy. So it's just heat. Enthalpy is heat with moles considered. Okay? So if I were to say, okay, indicate the sign change, so just the sign, that means positive or negative, of the enthalpy, H, change just means triangle, enthalpy change for the processes. And tell me whether it's endo or exothermic. So if an ice cube melts, that's because it absorbs heat, right? Heat goes into the ice cube and pulls the ice cube apart. So an ice cube melting would be a positive delta H. And because heat is going in, that's represented by endothermic. Whereas if you blow something up, okay, heat is released, combustion, given off. It feels hot to us. So the sign is negative because heat is lost and it leaves, right? So it's exothermic, heat exiting. So the signs, positive and negative, are going to be very important in this chapter in understanding which way the heat is flowing. Is it flowing into the reaction or is it leaving the reaction? Okay. So kids get kind of confused in this chapter because there's so many different ways to represent delta H, and I'm just going to write them all right here and then I'll kind of go through the slides. So sometimes they write it like this, delta H, and then they'll do this and they'll write RXN. This just means reaction because we're looking at chemical reactions, okay? And then sometimes they'll write it like this, where down here they write COMB, and all they're trying to tell you is that it's specifically a combustion reaction, okay? Now these are a little bit harder. These are for phase changes. So FUS is abbreviated for the word fusion. In English, does anybody know what the word fusion means? How about when you take two metals and you want to fuse them together, what do you do to them to get them to fuse together? You do combine them. It does mean combine. That's very, very good. How do you get two metals to combine? You have to melt them. So this enthalpy of fusion is for melting, because fusion is melting. So we'll get more into that when we do a practice problem. And then VAP is abbreviated for vaporization, aka evaporate, aka you're turning a liquid to a gas. So this is a solid to a liquid, right? That's what melting is. So this is why this is important, is that there is heat involved in phase changes, like solid to liquid, liquid to gas, gas to liquid, liquid to solid, as well as chemical reactions. So chemical reactions aren't the only types of processes that involve a heat exchange. Taking ice and melting it and then boiling it involves heat exchange. So those are phase changes, because you're not changing the identity of them, you're just changing what state of matter they're in. Now chemical reactions, you're changing who they are. That's the whole point of a chemical reaction. You start with some stuff and you end up with totally new stuff, okay? So that's like these guys up here. Oh, whoa, wait a second, sorry. What just happened? So that's like these guys. These guys right here are for phase changes, state of matter changes. Okay? They all mean the same thing though. The little subscript is just them trying to be more descriptive. Like, hey, what am I working with? Oh, if it's delta H of combustion, I'm probably working with a combustion reaction. Oh, if it's enthalpy of fusion, I'm probably just melting something. Okay? So, again, this is what I was just saying. So this is all vaporization, to evaporate something, and enthalpy of fusion is to melt something, which is what we just did on the other one, on the other slide. So what we're going to work with is what we're going to end with today, and we're going to practice these together, is heating and cooling curves. So for today, we're not going to look at chemical reactions. Today, we're going to just change phases, all right? And that's either by heating a substance up or cooling the substance down, one way or the other, okay? Now, this is an example of a heating curve of a substance, all right? So on the y-axis, you have temperature, and on the x-axis, you're just watching as the process proceeds. So right here, along this flat line right here is the substance's freezing point, whoever it is, whatever temperature it is. And along this flat line right here is where the substance starts to boil. It's its boiling point. So think about it. If you're below a substance's freezing point, it's a solid. If you're between freezing and boiling, it's a liquid. And if you've boiled it, it's a gas. That is the same for all sort of substances. Okay? So what happens is, along this curve, we're going to pretend this is water for right now. We're going to pretend this is water. What temperature does water freeze at in Celsius? Anybody know? 0. What temperature does water boil at in degrees Celsius?
4.18.
Nope, temperature, 100.
All right.
Okay, so look it. If water is below 0, it's a solid. If water is between 0 and 100, temperature-wise, it's a liquid. If you get water to be above 100, it turns into a gas. Okay, so what happens as we move around this curve, we go through different changes. All right, so I'm going to focus on the diagonal lines. And when I say diagonal lines, you see how this is diagonal, and this is diagonal, and this is diagonal, whereas the other two lines are flat. I'm just focusing on these lines. So if I want to move along these diagonal lines, up or down, if I'm moving on my graph, is temperature changing along a diagonal line? Like if I go from here to here, is temperature changing based on the graph? Yes. Do we have an equation that has temperature change in it? We do. We just learned it. It's MCAT. So the equation for this line right here is Q equals MC solid delta T. The equation for this line is Q equals MC liquid delta T. The equation for this line is Q equals MC gas delta T. So yes, even though we said water's specific heat is 4.184, that's only in the liquid phase. It's actually not that when it's in the solid or the gas phase. Now, what is it? I don't know right now, but I will give it to you. You don't have to memorize it. It'll be a constant that'll be given, okay? So all along these lines, the diagonal parts are MCAT. MC delta T, MC delta T, MC delta T. Why? Because temperature is changing. And that's our equation for heat when temperature is changing. So here's the confusing part. How come when you're taking water from a solid to a liquid, or a liquid to a gas, or backwards, gas to liquid, liquid to solid, how come the temperature doesn't change? And so that is confusing for most students. And the reason that is because when you take ice and it turns a little bit to a liquid, it starts melting. Until all of the ice has been melted and turns into a liquid, it can't heat up, which is weird in terms of temperature change. Its temperature doesn't change while it's converting from a solid all the way over to a liquid. And you go, well, that doesn't make any sense. Well, that is because of one reason. When you are going through a phase change, so you've taken ice, it's now at 0. At 0, you will have both liquid and solid water. You have both parts, okay? While it tries to transition to full liquid water. During that process, there's no heat involved. The heat is used not to change temperature, but to pull the molecule or substance apart. Right? Solids are rigid. So what happens is the heat comes in and it starts to pull the solid apart until it's all the way in its liquid phase. So that's where the heat goes. It goes to try to rip the thing apart to make it a liquid. Once it's fully a liquid, if you continue to heat it, it will change temperature. But during that actual crossover of trying to get the solid to turn into a liquid, there is no temperature change. Okay? So for example, water is held together by hydrogen bonds. So what the heat does is it goes in and it weakens the hydrogen bonds in the water molecules to spread the molecules further apart so that they can become a liquid. Okay? So because of that, the equation for this line right here, and right here cannot be MC delta T, because delta T is temperature change, and we just pointed out that there's no temperature change. So the equation for this line is the other one that has H in it. Q equals NH. Q equals NH. All right. Now we have two H's that we learned about phase changes. So this one down here, I'm going to erase all this. This is Q equals NH of fusion, because fusion means melting. And this one is Q equals NH of vaporization, because vaporization means evaporating, right? Liquid to gas is evaporating. So there are all of these equations all along this phase change line. Solid to liquid to gas. Now we're not going to do this today, but we can go backwards. We can condense, right, like gas to liquid, or we could freeze liquid to solid. But we're only going to work on going uphill today. Okay. I know this seems like a lot of equations all at once, but I promise you'll get good at it. It's not too bad. It seems a little overwhelming at first. I'm not going to go over this slide. This is everything I just said to you that I drew along the curve. You can use this as additional instruction points, okay? And we're not going to do cooling today, but you don't have to heat. You can remove heat by cooling. So that would be starting at a gas and bringing it back down to a solid. It's just the opposite of the other curve, okay? So in these types of problems, it says how much energy is needed to heat 25 grams of water from 20 degrees Celsius to 60. So here's how these problems start. Here's what you need to do. We need to get good at drawing the curves. What I mean by that is everybody do this. Okay? And then the curves will go like this. Up, over, up, over, up. Every time. Now, this is water. It said it's water in the problem. So this flat part right here is 0 degrees Celsius, because that's when water freezes. This flat part right here is the boiling point, so that will be 100 because my substance is water. Water freezes at 0. Why is it not? And boils at 100. And then what you do is you plot the two temperatures that are given. The two temperatures that were given were 20 and 60. So you go back to your graph and you go, okay, well, where's 20? Well, I'm doing approximation, right? So 20 is like right here, a little bit above 0. Where's 60? A little bit above halfway, right? Between 0 and 100. And you draw arrows between your two data points. So you start from your first dot and end with your second dot. So there's one arrow. When there's one arrow, there's only one equation that you have to use, which is really, 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 really nice. And what's that equation? Well, this is a temperature change. So this is Q equals MC delta T, where we're in the liquid phase, because between 0 and 100, water will be a liquid. And now we're trying to find energy or heat, right? Those words can be used interchangeably in this chapter. So we're trying to find Q. Okay? So let's see. I need mass. Did the problem give mass? Yes, 25 grams. All right, now the specific heat of liquid water, you will have a chart or you will get to look up. So if you look right here on my notes, and it's also in your book, and again, this will be posted. This says constants for water. These are all the constants you could need for water. So you don't have to memorize them, you just have to know how to use them. So the specific heat, this little c, of liquid water, this is an L, is 4.184 joules per gram degrees Celsius. So that's what we plug in for C. 4.184. It's a constant that we just looked up in a chart. So M, C. Now remember, the delta means final temperature minus initial temperature. So we have to go back to the problem. The final temperature is 60 minus the initial temperature is 20. So 60 minus 20 is 40. So 60 minus 20 degrees Celsius. And that's it. Now we just solve for it. So this is 2 sig figs right here, so your answer is going to be 2. The full number is 4184. Now let's look at units. Grams cancel, degrees Celsius cancel, and we're left with joules, which is good because Q is measured in joules. If we round to 2 sig figs, it's 4,200 joules, or you move the decimal 3 to the left to turn it into kilojoules. Now, this number is positive, right? What does positive mean? It means endothermic. What does endothermic mean? Heat going in. Think about it. You need to get water to change from 20 to 60. That's because you're going to have to put heat in. You're going to have to heat it up. Add heat. How would you do that at your house? You'd put it on a stove. You'd be putting heat into it from your stove to change it. Okay? So this is how much energy you got to put in to get that to happen. Questions? We're going to do a bunch of problems like this. So if you're struggling, it's okay. I promise you'll get better. All right, let's try the next one. How much energy is needed to heat 25 grams of water from 20 degrees Celsius to 120? Now, here's the problem. It is easy to want to do Q equals MC delta T because there is a delta T. But you will find when we map this out that it's going to be a lot more work than that. So, first thing you want to do, draw your curve like this. Draw your thing. So I'm going to move this over. Okay, and then you go diagonal, over, diagonal, over, diagonal, every time. And now this is water, right? So this flat part is 0, and this flat part is 100, because that is the temperature at which water freezes and which water boils. Now, was this starting at 20 again? So 20 degrees Celsius is right here, ish, right? Where is 120? Well, it's like up here somewhere, right? So you can't do this. It doesn't work like that. You have to stop at every intersection where the lines run into each other. Like what I mean by that is this. Here's my first dot, my starting point. I hit an intersection, so I have to stop my arrow there. And then I get over here and I hit another intersection and I have to stop my arrow there. And then I finally got to my final destination. It's like a road trip. At each point you have to stop. So the bummer part is when there's 3 arrows, there's 3 equations. There's the equation for this line, there's the equation for this line, And there's the equation for this line. That is because when you're taking water at 20, it's a liquid. Not only do you have to get it hot enough to boil, you have to get it all to boil, and then you have to keep heating it. So it's not that simple just to cut straight across. You're heating it till it boils, it starts boiling, and then you heat it past its boiling point. That involves a lot of work, okay? So let's just talk about what my 3 equations are going to be. So equation 1 is going to be the same equation as it just was. Q equals MC, I'm in my liquid phase, delta T, right? That's equation 1. Now, as we move, we just add the equations together. So plus, what's the equation for the flat part? Well, that one is NH vape. Q equals NH vaporization because we're evaporating from a liquid to a gas right here. Plus, what's this third equation? Well, we're changing temperature again, right? So MC, now we're in the gas phase, delta T. Okay, so let's just do the equation number 1. I'm going to do equation number 1 right here. So this is all Q equals, right? Q equals. What's mass? The mass was 25 grams, I think, again. 25 grams. Mass, check. What's the specific heat of liquid water? You need to go look it up. You don't have to memorize it, you just need to use it. And I'm going to tell you what it is because you can easily look it up. It is 4.184 joules per gram degrees Celsius. So C is done. Change in temperature. This is where you have to be careful. This equation right here is for this line. It's not for the whole thing. So you have to do the delta T for that. So what's the final temperature? Where does that arrow end? 100 is where this arrow ends. Minus, where did this arrow start? 20. So again, this equation is for this line. So you have to use the delta T for that arrow only. Now, I want to focus on units. Grams cancel. Degrees Celsius cancel. And you'll be left with joules. I'm not going to calculate it out yet. I'm just kind of showing you because there's going to be an issue. So next one is NH vaporization. And you go, what is H vaporization? Well, when you have access to this, you will see it's a number. You don't have to memorize it. I have it for you. You'll be able to plug and chug that number in. Okay? This is the enthalpy of vaporization for water. This is how much energy per mole is required to get water to turn into a gas. That's what vaporize means, liquid to gas. So, let's see. Oops. Here's the other part, though. What does N stand for? Moles, right? Did I give you moles? No, I gave you grams. So you have to turn grams into moles. It's not hard. 25 grams of water, and water is 18.02 grams per mole, right? 1 oxygen plus 2 hydrogens. So this right here is N. This is how you get N, grams to moles. So N is taken care of. And then this, you look up. I just did it, right? It was 40.8. Kilojoules per mole. So you'll notice that the moles now cancel out. Now there's a problem. Your first number comes out in joules, and this number comes out in kilojoules. You can't add two things that aren't in the same unit together. It's not possible. Well, it is, but your answer will be wrong. So I'm making the executive decision to change this one to joules. You could just as easily change the top one to kilojoules instead. They just have to be in the same unit. You can't have a joule and add it with a kilojoule. You either have to both be in joules or both be in kilojoules. I'm personally choosing to say for every 1 kilojoule there are 1,000 joules, so I can get my units to match. Now my kilojoules cancel and I'm left with joules. And I'm left with joules on the first equation as well. Okay, so that was equation 2. Now I have my last equation. So this one was number 2. Now I'm going to do equation number 3, which is this one, mc delta T. Well, this is actually a lot less work. What's my mass? 25 grams. Maybe I'll change that color. It's kind of hard to see. And then what is C, specific heat of water vapor? I don't know, but we can go look it up. So let's look it up together. You don't have to memorize it. Specific heat of water in the gas phase is this number. See, all these constants are for water. You don't have to memorize them. So 1.87 joules, 1.87 joules per gram degrees Celsius. And then delta T. So now let's be careful. That belongs to my third arrow only. So the final temperature of my third arrow is 120. Minus, where did my third arrow start? Be careful. What temperature, right here, did this start at? 100. Is that right? So yes, these are a little bit intense. And we're left with joules. So joules and joules and joules. Now, there are so many numbers on here. I highly suggest doing each one of these one at a time. Do the first one, write it out. Do the second one, write it out. Do the third one, write it out. And then you can add them all together. So that's what I'm going to do on this next part. I'm going to do equation number 1 and write it out. So 25 times 4.184 times 100 minus 20 is 80. So for equation number 1, I got 8,368 joules. Equation number 2 is 25 divided by the molar mass, 18.02, times 40.8, right here, times 1,000. Okay. Equation 3 is 25 times 1.87 times, what is 120 minus 10? Or 100, excuse me. It is 20. So for that one I got okay. Just add them together. Okay, it's a huge number. So I want you to round to 2 sig figs, so right here. So this would be 66,000 joules or 66 kilojoules. And positive, right? So endothermic Y, it's positive. Heat's being added or going in. If you want to take water at 100 or at 20 degrees Celsius and turn it into 120 degrees Celsius, you better believe you have to add heat to do that. This is how much. I'm going to try one more with you. Okay. Let's see. Last one. How much energy is needed to change 36 grams of water? So we changed the mass a little bit, but it's still, the substance is still water, from 25 degrees Celsius to steam at 100. This is just a wording thing. So the word steam means gas at 100. So when we go to draw our chart, I'll show you what that means. So again, we draw the lines, and we go up, over, up, over, up. It's like steps, you go up. Now this is water still, so this is 0. Oops. 0, and this is 100. Okay, 25 is like, I don't know, here-ish. And here's why this is confusing. There are 2 locations you can pick for water at 100. There's this intersection and this intersection. This intersection is liquid water at 100, and this intersection is gas or vapor at 100. Why? Well, because liquid is over here and gas is over here. So if you're over here, you're on the liquid side. If you're over here, you're on the gas side. So when it says steam at 100, you're going here, because that's by the gas side. Well, this one's kind of nice, though, because it's less arrows. Watch. I start at 25. I run into my first intersection. And then I only have to go to here. So 2 arrows is 2 equations. The equation for all the diagonal lines is Q equals MCL. I'm in the liquid phase, delta T. The equation for this flat line is Q equals NH. I don't have delta T in there, but I call this vape because I'm evaporating. So I calculate both these numbers and I add them together. I know I only have 1 minute. Please bear with me. Let's do this first one. The mass is 35 grams. Check. Specific heat of liquid water. I look up in my notes. It's this number. Don't have to memorize it. It's a constant. Delta T is for this arrow only. The final temperature of this arrow is 100. The arrow started at 25. Okay, first equation's done. We can calculate that out. Here, let's do it. 35 times 4.184 times 100 minus 25 is 75. This number comes out to be 1,000 or 10,983 joules. Please bear with me. So I have my first one done. Plus, now I need to do this one, okay? Q equals...
You got wrong mass. It's 36 grams.
Oh, is it 36?
Yeah.
Sorry, thank you. So let me recalculate. So this is 11296.8. Let me just finish the last one real quick, okay? So N means moles. I didn't give you moles. I gave you grams. So 36 grams divided by 18.02 grams per mole. This whole term right here is N. There's my N right here. And then enthalpy of vaporization, you have to look up. 40.8 kilojoules per mole. It's a constant. Moles cancel. Grams cancel. And I'm going to have the same issue here, where this top number comes out in joules, and this one would come out in kilojoules. So I'm going to change 1 kilojoule is 1,000 joules, so that I'm in the same unit. So 36 divided by 18.02 times 40.8 times 1,000, and you get this number for this equation is 81509.43 something something something. You add the two numbers together. Oh my. And you get, let's do right here.
Is it like 9,003, like 93,000?
Yeah, so I'm just writing the whole number right now. And with 2 sig figs, it'd be 93,000 joules. Or 93 kilojoules.